When a track athlete hits a full sprint, their body undergoes some of the most intense mechanical stress a biological system can endure. In the moment before the foot strikes the ground, kinetic energy builds, preparing to move directly up the leg. That impact generates a downward force, often measured at several times the athlete's total body weight. If you were to repeatedly slam a heavy machine into concrete with that same concentrated load, the material would eventually chip or fracture. We avoid that kind of structural failure because of how the human knee is built. It is an assembly of components designed specifically to manage these violent forces. To understand how it works, we have to look past the skin and treat the knee as a piece of physical hardware. The foundation is built on two heavy-duty pillars, the femur in the thigh and the tibia in the lower leg, which bear the bulk of the body's weight. At the front sits the patella, or kneecap. It acts as a physical shield for the interior joint. But the patella also serves as a mechanical lever. By shifting the tendon's path away from the joint, it changes the angle of the muscle's pull, which increases the leverage available to your leg muscles. While these bones provide a strong framework, placing them directly against each other under such high pressure would create enough friction to destroy the joint. The most critical point of the system is the small gap where these bone ends meet. To prevent the bones from grinding together, the surfaces are coated in articular cartilage, a biological material smoother than the surface of ice. Tucked between the bones are the menisci, two C-shaped pads acting as primary shock absorbers. When the foot strikes, downward weight compresses these pads outward, spreading kinetic energy. Once the load lifts, they immediately decompress, resetting the system. These dampeners protect the bones, but the joint would still be prone to buckling or sliding without a secure way to hold the entire assembly tightly in place. Maintaining alignment under stress requires a system of high-tensile cables. Inside the joint, the ACL and PCL cross over each other to form an internal brace. This configuration prevents the femur and tibia from twisting or sliding too far forward or back. On the outside, the MCL and LCL act as side stabilizers, preventing lateral collapse during directional changes. As the leg bends, these four ligaments tighten, creating a physical limit that prevents the joint from overextending. This network effectively transfers the load of your movement. It catches the energy of your stride and guides it down through the lower leg bones to be dispersed safely. The rigid bones, the smooth cartilage, and the strong ligaments work as a single, coordinated stability system, relying on each other to manage the body's weight. These interactions occur in fractions of a second, stabilizing our weight and absorbing physical shock every time we move. When we look at an athlete in motion, we are seeing those internal mechanics integrated back into the muscular leg. Every step you take is a result of this specific coordination between the solid bone, the cushioning cartilage, and the fibrous cables. Next time you climb a flight of stairs or go for a run, consider the constant adjustments and load-bearing happening inside your knees just to keep you moving. To see how other parts of the body manage the demands of daily life, subscribe to BioMotion 3D. We'll see you in the next episode.